Hi there, this is just a quick follow-on on my Kingshill V-series dual 150 volts power supply I showed recently. If you have not seen that, you should really watch it first. There's a link in the description. Unfortunately, I wasn't able to video many steps because I could only work on the power supply sporadically and with noisy fans blasting because of a heat wave. In that first video, I mentioned that I wasn't happy with the heat produced by the components producing the stabilized 18 volts or rather plus minus 9 volts for the control board. This heat is produced all the time, regardless of the load connected to the output, and mainly in the two Zener diodes, the current limiting resistor and the series transistor. The heat is kind of expected if you use Zener diodes, since these need a decent current going through them to produce the nominal voltage, and if the input is as high as here, more than 35 volts, the voltage drop times the current simply means a lot of heat. The only way to avoid this would be a complete redesign of the control circuit, at least as far as producing the operating voltage. I did not want to go that far and figured that things could be improved, at least somewhat, by simply using beefier Zener diodes that were mounted away from the PCB to get better cooling. The original Zener diodes are supposed to be of type VR9F, a diode with a nominal voltage of 9 volts at 20 milliamps and rated for 2.25 watts. But the watt rating of those on board may even be less, and they may not be VR9Fs, because they seem to be in a glass envelope and not in the metal can shown in the datasheet. As replacement, I picked the 1N5346B, a 5 watt type. Its nominal voltage is 9.1 volts at 150 milliamps, which is higher than the VR9F, but at 20 milliamps its voltage is close enough. The junction temperature is a maximum of 200 degrees Celsius, but of course the junction is always hotter than the case. The plan is to leave the leads as long as possible and raise the body from the PCB to maximize cooling. This was far easier said than done, as the diodes are physically much larger and tricky to get into the existing spacing of the PCB, plus the leads are thicker, so I had to drill the holes slightly wider. I used the right side power supply for this modification, doing one diode at a time and testing the unit in between, and this is when I made a stupid mistake. You see, to solder the diodes in, I folded the PCB backwards on its wiring harness, and transistor VT8 at the far corner of the PCB touched the heatsink somehow. Even though the power was off for some time, a mighty spark occurred because the large smoothing cap had still kept much of its 200 volts charge, and through the collectors of the power transistors, the heatsinks are directly connected to it. Needless to say, from then on I religiously discharged both power supply smoothing caps before doing any work. I'm using my own discharger here. The red LED shows which lead is positive, and when the light is out the cap is discharged safely. But the damage was done. The right power supply no longer worked. No output voltage at all. I replaced VT8, a BCY70 and the only PNP transistor in the circuit, and after that some output voltage was now produced, but less than 40 volts, even with the voltage control all the way to the right. I suspected the op-amp was damaged as well, but that turned out to be fine. What was damaged was diode MR4, the Zener diode producing the reference voltage. This is a type 1N823 and should produce 6.2 volts, but after the accident it was only doing about 1.5 volts. This was about 4 times too low, and as a consequence the output voltage was also 4 times lower than it should be. I considered replacing it with a cheap 6 volt Z diode, but in the end I decided to spring for the expensive real thing. Replacing the bad 1N823 with a new one fixed the right side unit. I also wanted to add a heatsink to VT9, a BFY50 in a TO39 package, but there was very little space available. The only type that could fit was this one, but it was too tall. It would interfere either with the components of the PCB or, when lifted away from the PCB, touch the upper enclosure of the power supply. My solution was to dremel it into 2 halves, one for each power supply. Each heatsink is now only about 5 mm tall, and while that reduces the effect, it's better than not having it. The thermal image shows that all that work had some effect. The hottest part with 88.8 degrees Celsius or 192 degrees Fahrenheit is now the current limiting resistor, which means the very hot Z diode is now less than that, a drop of at least 16 degrees Celsius or 29 degrees Fahrenheit. The transistor VT9 is also marginally cooler because of the heatsink. Satisfied with the result, I duplicated my efforts on the left side power supply to get it to the same state. Here is a view of the right side with the new diodes, the half heatsink on VT9, a new reference and the op-amp in the socket. The same changes on the left side. This one also got a new reference because I noticed that the old one instead of 6.2 volts produced just 6 volts. That meant the left side max voltage was slightly below 150 volts. The new reference fixed that as well. On that topic, I noticed that the analog meter on the right power supply was reading about 10 volts too high. I normally wouldn't bother with that, but it meant that at 150 volts output, the needle was hitting the stop at the right side, which can't be a good thing long term. The meter itself is a 100 millivolt or 500 microamp type, which means it has an internal resistance of 200 ohms. To run it at 150 volts, a series resistance is needed that drops the excess voltage of 150 volts minus 0.1 volt at the 500 microamps going through the meter. That calculates to 299,800 ohms, but we don't need to be that precise with these analog meters, and 300K is fine. In this power supply, they split the 300K into 250K resistors, one of which can be shortened using the volts times 2 momentary switch. Using a borescope camera, here is how that looks in reality. The resistors determining the voltage range of the analog instruments are the 250K, brown, green, yellow. One of them is across the volts times 2 switch. To make the meter read lower, I need to add more resistance in series, but how much is a try and error affair. It is very hard to get to this place with a soldering iron, so I snipped one of the leads of the more accessible 150K off. It would normally connect to the second contact of the switch on the left where the big red wire carrying the output voltage goes to. Cutting this connection allows me to use alligator clips to temporarily insert more resistance. With the alligator clips connected to the resistance box and that box set to 0 ohms, you can observe the original problem. I set 100 volts on the analog instruments, but the output is just shy of 92 volts. And setting the voltage to read 100 volts on the multimeter, the analog instrument is clearly beyond 100 volts. I can now add additional resistance until the analog meter reads 100. 10K. Yes, it's going the right direction. 20K, almost there. 30K, perfect. Changing the output to 150 volts and the meter with the additional 30K now shows that correctly. And dialing 50 volts on the analog meter gives 51.6 on the output. That kind of error is acceptable. Here is a 30K resistor soldered in series to make this adjustment permanent. I'm fully aware that I should have added 15K on each of the 150K resistors to keep the volts times 2 switch accurate, but soldering behind the front plate, especially on that switch, is very tricky. I could just about manage adding the 30K to the first 150K. I would have to dismantle pretty much the whole front, and since I'm not using the volts times 2 switch anyway, I decided not to do that. Here I'm selecting about 21 volts on the multimeter, which shows as 20 volts on the analog one. When I'm pressing the volts times 2 switch, I should see 40. But it's slightly lower, maybe about 37. That does not bother me. When I need a precise low voltage, I wouldn't use this 150 volt power supply in the first place. I did investigate changing the current measurement range from 1 amp to say 0.3 amp full scale. As it stands, the meter is shunted by a 0.1 ohm resistor diverting the excess current of 0.9995 amps around the meter. With the same calculation, 0.3 amp full range would need an increase of the shunt to 0.33 ohms. But in reality, the shunt arrangement looks very complicated, with 3 very low ohm resistors formed by wire loops in series and connected by 4 wires into the circuit. It's obviously doing more than just shunting the meter. It would take some effort to completely reverse engineer this arrangement, and therefore I decided to leave as is. And with that, I declared my work on this Kingshill V-series power supply done, and it's now ready for use. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.